Okay, then in today's magnetostatics part, we will discuss about the inductance concept, the self-inductance and the mutual inductance. And the mutual inductance concept, the basics I will be able to explain because this part you would have been already covered in your network theory. And the way it is some simple, nothing but your network analysis. And the next thing is a magnetic circuit, which is very important for electrical people and then for other competitive examinations also. And then we will discuss the Faraday's law. So these are the topics for today. First of all, we will discuss about the self-inductance. Self-inductance is nothing but the inductance associated with the magnetic core itself. So which means that you can see in the example, suppose if you have an inductor and when you try to connect the inductor to a voltage source, there will be a current. And whenever you pass on current, there will be a flux which will be generated within this magnetic core. So the inductor is basically made up of a magnetic core which is surrounded by some number of windings, right? So those windings extremities will be connected to the voltage source. So whatever the current you are passing, that will actually develop the flux within the magnetic core. So in this case, how the self-inductance is defined was, so the amount of the flux you are passing is directly proportional to the current passing through the core. So you know that the total magnetic flux can be written as the self-inductance times I. So the basic definition for current is nothing but what will be the total flux generated within the core divided by the current I. So the self-inductance of this is nothing but how much flux is developed within the core divided by the current passing through the core. So that is the basic definition for your self-inductance. And sometimes that the total flux is basically said to be the flux linkage, as I mentioned. That is the n number of windings into the flux per each turn. So sometimes you are able to capture the flux per one turn. If you want to calculate the total flux, you should multiply that each flux per one turn by n number of windings to get the total flux. So whatever the self-inductance you are defining, you should be careful. This is the total flux generated within the core divided by the amount of current you are passing. So it is the same way how I have defined the capacitor. Suppose if you have a capacitor and you apply a voltage here, what will happen? The charge will be induced on the capacitor. The charge is directly proportional to the voltage. So I can say Q is equal to C into V. So in the same fashion, the amount of the current, whatever you are passing, defines how much flux is developed here. So the flux is proportional to the current. The proportionality constant, voltage source is taken as sinusoidal source. Yes, of course. But sometimes you can apply the DC also. That is not a problem. But DC, what will happen? Inductor is going to behave like a short circuit. That's it. So whatever I was talking about is a sinusoidal. Yes. So the self-inductance is defined as the total flux divided by the. Okay, you understood the definition of inductance now, everyone? Yeah. So we will see the practical cases. We'll try to find out the inductance of a simple configurations like solenoid, toroid, and then we will go to the coaxial cable. But the basic definition, you have to keep it in mind. The inductance is nothing but this formula. You have to remember. The flux generated divided by the current. So that is the basic definition for self-inductance. So the meaning of self indicates that the flux generated within the core is due to the current passing through within the core itself. So the inductance is purely because of this current is flowing through this core itself. That is the reason why I was calling it as a self-inductance. Suppose if the current is flowing in another coil and that produces the voltage in the primary coil, something like a transformer, we can call it as a mutual inductance. That will come across later. So the first thing is the inductance of the solenoid. So you try to understand what do you mean by a solenoid. So solenoid is nothing but, you can see this is a kind of magnetic core. So you can see the shaded portion like this. This is a magnetic core, and this magnetic core is surrounded by n number of windings. So I have applied a voltage source here. So there will be current flow in this loop. You can see here, this is the way how the current is flowing. Now, all of you start with your right hand, Fleming's right hand principle, you can use that. So the current is flowing in this fashion like this. So you can see here current is flowing here and going back side of the core and coming back and again going back and going front like this. So it is making a circular loop like this. So can you tell me what will be the direction of magnetic field in this case? In which direction the magnetic field will be oriented? Start with your right hand and make sure that the location of all other fingers except the thumb should match to the current. Then the thumb is pointing in which direction? Is it upside or downside? Good. Because when you start with your right hand and make the rotation of your other fingers, then the thumb is pointing out. So then the thumb is pointing upside. So there will be a flux which will be developed on the axis of the solenoid. So there will be a flux which will be flowing perpendicular and it is parallel to the axis of the solenoid. Now, when you take any point which is outside the solenoid, will there be any magnetic field? So the first thing was, this is my solenoid and you have done some number of things like this. Okay, now I taken a point which is completely outside. Do you have any magnetic field which lies outside the solenoid? No. Can you tell me what is the reason? Can you tell me what is the reason? Magnetic flux direction. No. Can you put it specifically? So I will tell you one simple reason. Suppose I want to find out the magnetic field intensity outside the solenoid. So you can make use of the Ampere's law. So let me take a small loop which is something like this. So when you take a loop something like this, you are going to capture this current which is flowing in the clockwise, and you can see on the top side of the solenoid. And there will be some small portion which is going on the back side, right? That will be in the anti-clockwise. So what will happen when you take a loop like this clockwise and anti-clockwise, everything gets cancelled. You got my point here? So what I was saying here, when you take a loop something outside like this, you are going to capture the current on the front side as well as on the back side. So because the same current is getting circulated, the net effect will be zero. You got my point, everybody? So when you take a loop which is outside and your solenoid is inside, that case what will happen? Whatever the current which is flowing on the top side and whatever the current flowing on the back side, which will be exactly equal and opposite direction. So it will get cancelled. So you don't have, using your Ampere's law, what you will have? Integral H dot dl is equal to I enclosed. So when you see on the upper side, the current direction is one thing. On the below the solenoid, you will have a different direction. So your current will be zero. So since your current is zero, you don't have a magnetic field. So you got my point, everybody? So when you have any solenoid, the magnetic flux will be confined to core itself. When you are going outside the core, there will not be any magnetic field. So the reason was, when you take any point outside the magnet, whatever is flowing on the top side, the same thing is getting written back on the other side. So hence the net current will be zero. So you will not be able to have any magnetic field. So any questions here? So what I mean to say, when you are moving from D to C, there will not be any magnetic field because you are moving outside the solenoid. That point you have to remember. Now, So let me consider the loop something like this. I was starting from A, B, C, D, and again back to A. So what is your Ampere's law says? Integral H dot dl in a closed loop I enclosed. Okay. So first of all, what is the condition when you are going from A to B? You are having a certain magnetic field, right? Because you are going inside the core. So whatever the loop I have taken, A to B I have considered inside the core, and B to C everything will be outside. So when you are moving from A to B, there will be a magnetic field, and you have covered a length which is equal to the length of the solenoid. So I have given L is the length of the solenoid. So that is the total line integral here. And when you are moving from B to C, as I said, both the points are outside. You don't have any magnetic field. And when you are moving from C to D also, moving outside, there is no magnetic field. D to A also, there will not be anything. So when you are making a complete loop from A to B, C, and again D back to A, all other integrals are zero except the integral from A to B. Hence, the total line integral will be h into the length of the solenoid is equal to. So can you tell me what is the current which you are enclosing when you are moving from A to B? What will be the total enclosed current when you are moving from A to B?
Sir,
Ni.
N
Very good.
into I.
Correct. Good. Because you are able to cross all these loops n number of times. So each loop is carrying a current of I. So the total current will be N into I. So inside a solenoid, the magnetic field intensity is basically given by N into I divided by L. So this is your magnitude. And as I mentioned, the direction will be, so the direction of magnetic field will be something like this, which will be perpendicular to the solenoid. You can see here, parallel to the solenoidal axis. So the magnetic field will be something like this, and current will be circulating. So this is the magnitude part. Now, what is the basic definition for inductance I given? So the inductance is nothing but the magnetic flux divided by the current. Okay. Now, I know what is the current I was passing. So to calculate the inductance, I should know what will be the total flux. So to calculate the total flux, I can make use of the formula. What is the total flux formula in terms of flux density? Can you tell me what is the total flux in terms of the flux density? If you know the flux density, magnetic flux density, how will you capture the total flux? Perpendicular length. No, I was asking what is the formula for the magnetic flux if you know the magnetic flux density?
Into area, sir, then.
Yeah, the flux density multiplied by the area. Can you tell me in this case what is the area you have to consider? Will you take the surface area of this solenoid, or you will take the only the circular cross section?
Circular cross section.
What will be the reason?
Sir, because all the flux are axial.
X. Because the flux is contained in this direction, you should always take the area in this case. See this particular direction of this surface, this is also pointing in the same direction. So when you see using your magnetic flux, you are having double integral B dot ds, right? So if you consider this surface, the direction of this surface and the direction of magnetic flux both are in the same direction. Then only you will have a magnetic flux. So suppose what you will have if you are moving parallel to the surface. So let us say this is my surface area. So in that case, the direction will be pointing here. So that time your flux will be upward and the surface is like this. So both are perpendicular. You will not have any flux. So when you want to have a finite amount of the flux, the area also should be chosen in the direction of the flux. So the magnetic field is here. So you should take the circular area of cross section. So if R is the radius of the solenoid, so the area you can define it as pi r square. Okay, but as of now I was defining it as A itself. So the A value is nothing but pi r square. keeping it in mind, R is the radius of the solenoid. So you know that in turn, the flux density is mu into H into A. So B is equal to mu H. So that will be is equal to mu into the magnetic field intensity, you know, that is equal to Ni by L into A. So just now you can see this equation I have substituted there. So this is a flux per each turn. So what is the flux linkage then? The flux linkage will be n number of windings into the flux per each turn. So the flux linkage is also said to be the total flux. Is equal to, you multiply this one with a n, the flux per each turn with n. So you are going to have n square mu A by L into I. So it is of the form phi total is equal to L into I. It is of the form. So what will be the inductance we are giving here? That will be mu A divided by L. So this represents the inductance of your solenoid. So where A is nothing but area of cross section. So that is nothing but your circular area. And L is nothing but the length of solenoid. So I will tell you one simple thing. When you want to find the inductance, you should start with magnetic field intensity. So first of all, you find out what is the magnetic field intensity. Once you know the magnetic field intensity, you know the flux, because the flux is nothing but B into A. So you will be able to define the flux per each turn. So then calculate the total flux linkage. Then you can define the inductance something like this. The total flux divided by the current. So this is an approach you have to follow if you are doing the inductance. So any doubts in approaching this process? So if this is understand, the next configuration you should be able to do. So any questions you have, you try to clarify it now only. So do you have any questions now?
Sir, why we didn't consider twice the area like we do?
Twice the area means?
Because both up and down cross section.
No, this is not the total flux, because that you will do when you are doing this relation, right? So double integral B dot ds is equal to 0. That time you are considering how many surfaces the flux is coming out. Here I was not calculating that. I was calculating in one turn how much flux is contained.
Yes.
So my point is restricted there, confined there. So
Okay.
what you are saying was this case, right?
Yeah, because we did two also.
This is actually when you are doing in the boundary condition,
Okay.
right? This we are doing. So generally when you are taking the closed surface, the flux will be 0. But what in this case I was finding, I was taking a small loop. In that loop, how much flux is contained?
Yes, sir. Yes.
So that is nothing but the flux density which is existing into the area of the loop.
Okay. Yes, sir.
Yeah. Okay, then we will go to the next case now. This formula you have to remember. This is the inductance of the solenoid. Yeah. Next one is the inductance of the toroid. So toroid means nothing but nothing but a circular kind of magnetic core. You can see the diagram. So this is your toroid. So I was passing a current here. So you can see here the current is passing on the front side and going back and coming front. So it is making a circular loop something like this. And it is making a complete rotation and it is coming out. So whatever the current which is here will be coming out here. So you are going to connect a voltage source between these two. So the same thing, when you are passing a current here, can you tell me in which direction the magnetic field will be produced? Suppose you take this point of entry, okay? You take this point of entry, you start with your right hand, making sure that other than thumb, you should, whatever the other fingers are there, you should match to this direction. You should start with your right hand, place other fingers, all other fingers in the same direction of this current. Then the thumb is pointing which side? The thumb is pointing something like this, correct? So in the same way, if you place all other fingers matching to this, the thumb is pointing like this. Similarly, when you place all other fingers like this, thumb is pointing like this. So you join all those points. So in which direction the flux is contained? So it will be along the circumferential length of the toroid. You got my point or not? So at each direction of the current, you trace the magnetic field direction. If the current is flowing, the magnetic field will be like this. If the current is like this, magnetic field will be similarly like this. And if the current is flowing like this. So when you trace all these things, you can see that the magnetic field is confined along the circumferential length of this toroid. So you got my point here? So when the current is flowing, the magnetic field will be concentrated along the circumferential length of this toroid. Will you agree with my point or not?
Yes, sir.
Yeah. Then in that loop, you find out what is the total line integral of the magnetic field intensity. So as I said here, if you see here, this is the inner portion and this is my outer edge. So this is my inner edge of the toroid. So that is at a distance of B. Okay. And the outer edge is at a distance of, sorry, it's the other way. The inner edge is at a distance of A and the outer edge is at a distance of B from the center of the toroid. Now, what you do, you take a loop within the toroid itself and having a radius of R. So in that case, what is your Ampere's law says? You find out, what I was asking you was, you find out the line integral of the magnetic field intensity in this particular loop, which is inside the core having a radius of R. So that is equal to the current which is enclosed. So can you tell me what is the magnetic field intensity in that case now? So our approach is same, irrespective of whatever the magnetic circuit it is. So first find the magnetic field intensity. So in this case, can anybody say what will be the magnetic field intensity? You can switch on your mic and you can say.
Sir, in this case, the current will be like proportional to area.
No. What will happen? See, when you are going from here in this particular loop, how many number of times you are enclosing the current?
n number.
Same thing, n number of windings, right? Because the toroid is having n times. So when you are doing in this particular loop, the current will be always, how many number of times current will be coming into picture right now? N number of times.
Then ni by 2 pi that radius. Okay.
Exactly, right. So when you are going in this particular loop, the total circumferential length you have covered is nothing but 2 pi r.
Yes.
Is equal to the total current is nothing but Ni. Same thing. So instead of in a solenoid where you are making the windings in an axis. So here you are making a windings in a circular fashion, but it doesn't matter. You are covering the toroid with n number of turns. So the total current will be Ni. So now you go ahead and tell me the inductance value. Now you can see here, whatever the area I was defining. So if you see the area of this one, in this particular area only the flux is contained. The flux cannot be here, the flux cannot be here. Again, the same reason. When you take a nib point outside that, you will be able to capture the front side as well as the return current. So the flux will not be there, even if we consider here or even if we consider here. So the total flux will be contained within this area. Okay, so you can keep it in mind and go ahead. So what is the magnetic field intensity you got? That is equal to Ni divided by 2 pi r. So take it as equation 1. So the next thing, the flux per each turn is equal to the flux density into area. So that area I was calling it as this circular area of cross section. Can you tell me what is that area specifically speaking? So this is your inner edge and this is your outer edge. So what is the area of this shaded portion?
Pi b square minus pi a square.
Very good. Yes. So that will be the total complete outer circle area minus pi b square minus pi a square. So anyhow, that I was representing it as a capital A. So H is equal to Ni by 2 pi r, and the flux per each turn is equal to the flux density multiplied with area. So the flux per each turn is equal to mu H into A. So mu into Ni divided by 2 pi r into A. So what will be the total flux linkage now? So the total flux linkage is basically equal to the number of windings into the flux per each turn. So what you are going to get in that case, N square mu A divided by 2 pi r into I. You can correct me if I am wrong. So you can compare these two equations. This is of the form the total flux is equal to L into I. So by comparing, the inductance of the toroid is given as N square mu A divided by 2 pi r. So r is nothing but the distance from the midpoint of the toroid to the center. So can you tell me how to calculate the r value in that case? That means what is this is the midpoint, then only the approximation will be valid, or you can say that it will be error will be minimum. So what will be the distance from here to the midpoint? So can you tell me what is the value? So you know that this is A and this is B. So what will be the midpoint distance?
A plus b minus a by 2.
A plus
B minus a by 2.
why B minus A again?
Because that length is b minus a and we are reaching the midpoint of it.
No. I was asking what is the distance of this loop from the center itself?
It will be
A plus B by 2.
yes, sir.
Very good. A
B
plus B
by
by 2, right? If A is equal to 3 and B is equal to 5, so where is the
yeah,
midpoint lies there?
yes, sir. If
4,
I
right?
simplify that, then it is coming a plus b by 2.
Yeah,
Yes, sir.
it is simple. So it is simply nothing but A plus B by 2. This is an approximation. So where you can get error free. Generally, if the toroid is having a lesser circular area of cross section, you can straight away take it as A or B. If A is approaches to B means you can say R is nothing but A itself, right? If suppose A is exactly equal to B means your R is same as your A. So if the thickness of the toroid is much lesser, you can consider instead of R you can consider A itself. Okay. So shall I go to the next one then? Then you can see here inductance of a coaxial cable. So we have seen the capacitance in the previous electrostatics part. So now we will see the inductance of a coaxial cable. So the first thing was the inductance coming into picture when there is a magnetic flux. So similarly, the capacitance coming into picture when there is an electric field. So first of all, where will be the magnetic field in a coaxial cable? Did you remember what I said? When you consider any which is the coaxial cable, do you have any magnetic field?
Hello. We do not have
Yeah.
anything outside the field. The
The
cable.
magnetic field is there. Where is the magnetic field present in that case?
It is between the inner and outer.
What about when it is inside?
The
When it is
inside A
inside the inner conductor?
0, sir, because no current enclosed in it.
No, you forgetted the complete concept. Huh? What I told you, you go back to the coaxial cable. What I told you
Yeah,
in
means
case of coaxial
inside
cable.
that is between A and B. It is there.
What
It
about
is
within
written
A itself?
Within A, it will not be there.
Are you sure?
Yeah, it will be there. So it's distributed uniformly. Yes, sir.
Exactly. That's what I was telling you. When you are having an inner conductor, this is a number of wires which will be in a dense medium, right? Whatever you are saying is an electric field, because when you have a conductor, there will not be any electric field inside. But when it comes to the
Yes, yes.
magnetic field, yeah, the inner conductor is completely dense, right? So when you take a small loop in this, there will be a current. That current I already told you. The original current divided by the ratio of the areas. This is the total current enclosed. So I have given this equation also. You have seen the magnetic field profile. If you see within the inner conductor, it is linearly increases up to A, and after A, it will going to decrease. And when you cross B, it will be 0. So you need to do revision.
Yes, sir. Yes, sir. Sorry, sir.
Okay, no problem, no problem. Yeah. So, but still, anyhow, I am not going to consider what is there within the inner conductor. So let us say you know that the magnetic field is confined. Yeah, somebody is having question. Okay. So going to consider there will be a magnetic field which is present between the inner conductor and outer conductor, right? So first of all, what is the formula I given for magnetic field intensity? So between an inner conductor and outer conductor, the magnetic field intensity formula I have already given. You can go through that. I by 2 pi rho. If you consider any point somewhere here at a distance of rho, so I have told you just assume a Gaussian, you assume an imaginary loop, find out what is the current enclosed. So the current divided by the circumferential length is nothing but the magnetic field intensity. Since this exercise we already done, straight away I will take this equation. So between A and B, you will have this magnetic field. So you can calculate what is the flux. So the flux is nothing but the flux density multiplied by the area. So you can see here the flux is contained within this area. When you go between inner conductor and outer conductor, the flux is contained within this area. So that is the reason why, let me take the flux density multiply with ds, b dot ds. And for an instance, you can assume that the axis of the coaxial cable is z-axis. So in that case, the magnetic field will be there in which direction? So you have a current which is flowing along z-axis. What will be the direction of magnetic field? So even in a coaxial cable also, if assume that the current is flowing in z direction, can you tell me what will be the direction of magnetic field? Are you hearing me? No, rho. It's not rho. It's a simple again. It's a basic question I was asking, and you are still hesitating to say means. So the current is flowing in the z-axis. What will be the direction of magnetic field? The first class question in the magnetostatics. This is the first part.
Phi.
Phi, sir. Yes, sir. Phi.
Yes, it will be in phi. Why you are thinking so much time here? Taking so much time. So when you are having any current carrying conductor, the flux will be around that. It's a basic concept. You should not take this much time. So the magnetic flux will be phi direction. Now, if you want to capture the total flux, you should consider a surface where there will be a magnetic field. So since the magnetic field is there in the phi direction, you should also consider the direction of the surface in the same direction of phi. So which means that, so what is the surface you are going to consider? So the direction of this surface is also should be same as phi. So did you remember what is the surface area which is having a value of phi is constant? So in case of a cylindrical system, what is the differential surface area for phi is equal to constant? You can switch on your
Sir,
mic and speak, no problem.
yes, sir. It will be rho and dz.
Yeah. So what is the scaling factors?
Sir, it will be 1, sir, because
1
it
and
is
1.
Yeah.
Correct? Other
yes, sir.
person? So the magnetic, the surface will be, yeah, it will be d rho into dz. No factor, right? So this is the surface you have to consider. You may ask why I should not consider the surface in rho direction. So it's meaningless. If you take a surface in rho direction and the flux in phi direction, so the dot product will be 0. So you may have a finite amount of flux if you consider the surface in the same direction of magnetic field. Then you can go ahead now. So phi is equal to double integral mu h, direction will be a phi, dot product with d rho dz a phi cap. So a phi dot a phi is 1. So simplify that. Mu h is nothing but I by 2 pi rho d rho dz. So rho you can see here, when you are going in this particular area, rho is varying from this point to this point. So this is nothing but A to B. So rho is varying from A to B, and on the z axis you are moving on the entire length of the coaxial cable. So along the z direction you can integrate from 0 to L. So you can simplify that. What you are going to get? Mu I by 2 pi. So integration of 1 by rho will be ln of rho from A to B. And integration of dz straight away you can get constant. So that will be the length. So what you are going to get right now? Mu I by 2 pi L into ln of B minus ln of A. So ln of B minus ln of A, you can call it as ln of B by A. So you can see here, this is nothing but your L into I. So what is the inductance right now? You can define the flux divided by I is equal to mu by 2 pi into L into ln of B by A. So this is your equation for inductance in a coaxial cable. So understood the procedure? Anything you want me to explain again here?
Yes, sir.
So did you remember what is the equation for the capacitance in a coaxial cable? Can you say what is the equation for capacitance in a coaxial cable? You can switch on your microphone and tell. So I told you in the last class only you are not following up the class. So that is a problem. It's a problem for both parties. So by this time you should have been very familiar with the of these things and all. So have you revised everybody first of all? Are you going through the class once it get finished, or simply with a blank mind you are coming to the next class and attending? So you can answer me. So nobody wants to answer. So what is my observation was you people are not going through the classes. Simply, actually, I was putting so much of effort, and then you are not making use of it. So as soon as the class is getting over, I was trying to upload all these PDFs in the drive so that it will be easy for you to refer that. It will be like a quick reference, and you are not making use of it. Actually, it's a big problem, you know. So I want to know what difficulty you are facing. We can discuss the actual difficulty you are facing in this subject. So is it related to the way of explaining or your preparation? So where there is a fault? Am I audible for everyone? Okay, you've
Yes, sir.
seen the induct. Yeah, good. So next thing, we'll see the mutual inductance right now. So to understand that, you can see here, this is a magnetic core and I have done two set of windings. So this is my first set of winding. I can call it as coil 1. And this is my second set of winding, which is coil 2. So for the understanding purpose, I have assumed that both the coils are having equal number of turns. And there is a current which is passing through that. So what will happen when you pass some current here, there will be certain amount of flux which will be generated in this core and there will be certain amount of flux which will be generated within this core. So coil 1 is also having some self flux which is generated and this is also having some amount of flux. And what will happen since both coil 1 and coil 2 are nearby, whatever the flux generated from the coil 2 can also couple to coil 1. So what will happen in that case, in addition to the self flux which is generated within this core, this coil 2 also is going to create an additional flux in the circuit. So that additional flux when you are having, so the inductance value is going to be changed. So that I was calling it as a mutual inductance. So the mutual inductance comes into the picture when there is a coupling of the flux from one coil to the other coil. So in the same way, there will be some amount of flux which is linking to coil 2. So whenever the flux is getting additive, the inductance value is going to be changed. So first, based upon our understanding, I can define the self-inductance first, then I will discuss mutual inductance. So the self-inductance of coil 1, I can define it something like this. So initially you can take it as N1 and N2, number of windings N1 and N2. So in that case, what will happen in the self-inductance? The total flux linkage divided by the current. So I can assume a different current also, I1 and I2. But ideally speaking, since both are connected in series, I1, I2 is equal to I. So just to make it separate, the analysis, I was assuming that I1 is the current flowing through coil 1 and I2 is the current flowing through coil 2. Then the self-inductance of the first coil is defined as the total flux linkage divided by the current. So what is the total flux linkage here? The number of windings into the flux per each turn. So N1 into phi1 divided by I1. This is the self-inductance of coil 1. And what is the self-inductance of coil 2? N2 into the flux generated within the core 2 divided by the current I2. But ideally speaking, I1 and I2 will be same. How the mutual inductance is defined right now? The mutual inductance between the first and second coil will be defined as, so what I was defining here. So there is some amount of flux which will be going from coil 1 to coil 2. Okay, so for the mutual inductance, what is my cause is nothing but the flux causing from coil 1 to coil 2. So there is some amount of flux which is linking from coil 1 to coil 2. That I was calling it as 1, 2. So which means that the flux is coming from 1 and it is going into coil 2. So that case, how to define the mutual inductance now? So ultimately the destination is the coil 2. So what should be the number of windings I should consider in that case? So how to define M12? M12 is the mutual inductance because of the flux linkage from coil 1 to coil 2. So ultimately the destination is in coil 2. So the M12 can be defined as number of windings in the second coil into the flux linkage from 1 to 2. That means how much amount of flux is linking from 1 to 2 divided by, actually this flux linkage from 1 to 2 is happening because of the current flowing through coil 1. So I can define it as the phi 12 is basically the reason why whatever the current flowing in the coil 1 is going to create a flux in the coil 2. So the basic cause is I1. So can you tell me what is the value of M21? The mutual inductance from second to first. So you can switch on your microphone and at least one person can say.
Yes, sir. It will be N1 521.
N1, number of windings first coil into the flux linkage from second to first divided by, and the flux linkage from second to 1 comes because of what current?
I2.
I1 comes because of the second current, sir.
Second current, I2. Good. Okay. So is the definitions clear right now? Same definition. Mutual inductance is also same as the inductance, but the flux is due to the coupling from one coil to the other coil. Now, what will happen? Suppose if I say that if both the coils are identical, and both are placed very nearby. In that case, what will happen? Whatever the flux linkage from 1 to 2, you can say the amount of flux linking from 2 to 1. If both the coils are identical and the same current is passing. Means that what I was saying, I1 is equal to I2 is equal to I. Then in that case, what will happen? If both the coils are nearby, whatever the linkage from 1 to 2, the same thing is the flux coming from 2 to 1. So let me call it as sum phi. Then in that case, how this mutual inductance can be defined? So I can say M12 into M21 can be defined as, you multiply those two. So what you are going to get, N1, N2, phi 12 is 1. So I can call it as phi itself, phi into phi divided by I1 into I2. So when you say the flux from 1 to 2 remains same from 2 to 1, so your mutual inductance also same. So M12 will be same as your M21. So let me call it as M. So in that case, what will happen? This is also M, this is also M. So in that case, what you are going to get, M square is equal to N1 phi divided by I1 into N2 phi divided by I2. So whatever this thing is there, I was segregating. So something like this. And I was rearranging the equation. So why I was rearranging the equation was something like this, because this can be defined as the self-inductance of coil 1. And this is my self-inductance of coil 2. So the mutual inductance will be defined as root over L1 into L2. So this is the formula for your mutual inductance. And rest of the things I don't want to discuss here because you are going to study in your network theory. What will happen when two coils connected in series? So that will be equivalent will be L1 plus L2 plus 2M. So that things and all you will study in your networks. But here the concept of mutual inductance you should be able to understand. And this equation is true by assuming that the total amount of flux is linking from coil 2 to coil 1. So that you get as a coupling factor. So if you are assuming that 100% of flux is coupling from coil 2 to coil 1, then only this relation is true. Because whatever we have assumed here, this is valid by assuming that both the coils are nearby. So when both the coils are nearby, what will happen? Whatever the flux generated due to the coil 2, everything will be coupled to coil 1. So that you are calling it as a coupling coefficient, right? So ideally speaking, the mutual coefficient inductance will be K into root over L1, L2. So this K is nothing but your coefficient of coupling. So in this case, since I have assumed 100% coefficient, you can say K is equal to 1. So sometimes what will happen? You may have a coil 1 here, coil 2 here. So if 80% of the flux is linking from coil 2 to coil 1, so you can consider K is nothing but 0.8. So as long as both the coils are nearby, 100% coupling can be expected. So that time the mutual inductance is equal to root over L1 into L2. So you can ask any questions. If anything needs to be clarified, I can explain here now. Okay, next thing we will go to the magnetic circuits. This is very interesting topic. So it is same as your electric circuits. So when you go for the magnetic fields, all those magnetic analysis can also be done using your circuit analysis. So how to convert a physical magnetic circuit and you can model it in terms of your electrical circuit so that you can apply your Ohm's law, KVL, KCL even in the magnetic fields also. So whatever the Ohm's law you studied in electrostatics, V is equal to V equal to RI. So the same thing, same concepts you can apply in the magnetic circuit. That is possible when you are able to represent a particular magnetic circuit in terms of a circuit model. That means you need to model your magnetic circuit in terms of your network related circuit. So that we will try to see how to model the magnetic circuit. So if you want to model a magnetic circuit, so let us recollect what is a magnetic circuit means. The magnetic circuit is nothing but you have a magnetic core. The magnetic core is surrounded by n number of windings. So this magnetic core may be a solenoid and the magnetic core may be a toroid or it can be a coaxial cable. It can be anything. Or there are different shapes of magnetic cores are available. So when you see the configuration of a magnetic circuit, a magnetic core surrounded by a certain number of windings, so which will be connected to a voltage source. So in this case, what will happen? So based on the voltage you are connecting, there will be a current flow. There will be a current flow. So when you want to analyze the magnetic circuit, here you have to understand some of the parameters. That is the magnetomotive force. So the magnetomotive force is basically defined as the strength of the magnetic core to create the magnetic field. That means if I say a particular magnetic core is having a higher value of MMF, magnetomotive force, which means that when you pass a finite amount of current, because the core is having high permeability, it will be able to create more magnetic field intensity. So the magnetomotive force is the strength of the magnetic core to create the magnetic field intensity. So mathematically speaking, the magnetomotive force is defined as the line integral of magnetic field along the length of the core. So can you tell me what is the magnetic field intensity along the length of the core? So when you are doing it, the line integral from A to B, what is the value you are going to get? So it is nothing but I enclosed, isn't it? So when you are going from A to B, you are enclosing the solenoid by n number of windings. So the magnetomotive force is simply nothing but your total enclosed current. Can you tell me what is the value in this case? So when you are going from A to B, what will be the total enclosed current?
Sir, is it Ni?
Nice.
Correct. Yeah, N into I. So the magnetomotive force is nothing but Ni only. So that's what you can see the definition. So if N and I will be high, your magnetic field will be high using this equation. So the magnetomotive force is the measure of the magnetic core, and or you can say the strength of the magnetic core to create the magnetic field. So if you pass more number of windings, MMF will be high. If you pass a more current, your magnetic field will be high. So that's how your MMF defines. Is it clear? The first parameter, magnetomotive force, it is same as your electromotive force. How will you define electromotive force? Electromotive force is nothing but voltage in your electrostatics. Did you remember when I was discussing the electric potential, the electromotive force is basically defined as the line integral of electric field along a particular line. So the line integral of electric field is nothing but EMF. The line integral of magnetic field is called MMF. I hope the concepts are clear. And then now you can see here. So in case of a solenoid, what is the MMF? It's nothing but the number of windings into current per each turn. That is same as. So when you are going from A to B, you are covering a length of the solenoid. So this is same as your h into d. Correct? If you are finding the line integral, you can say h is a common outside, and the total length from A to B is nothing but d. So how the MMF can be defined? That will be n into I, or it can be called as h into d. So this is equation 1.
That this HDL means it is not a closed loop. Uh, this length we are doing okay. We are doing only from A to B. Okay. Yes, sir. Got it. Hello.
Okay, now am I audible for everyone? Am I
Yes,
audible
sir.
now? Yeah, someone has taken my status. I don't know how it is happened.
Yeah, I also saw like if we click on that action icon, then we can take it.
No, will it happen like that?
Yeah, it's saying we can take it.
Oh, is it? Okay. Anyhow, so we'll discuss now. So the magnetomotive force is nothing but the strength of the magnetic core to create the magnetic field intensity. So the MMF can be defined as so h into the length of the solenoid, or you can say n into I. Then, so we'll see the flux per each turn. So what will be the flux generated per each turn equal to the flux density into area. We can say mu times h into A, and take it as equation 1, this one. So the flux phi is equal to mu A into the magnetic field intensity can be written as the magnetomotive force divided by the length of solenoid. So using your equation 1, h can be written as MMF divided by the length of solenoid.
Sir, so generally we
Yeah,
do that h dot dl is equal to I enclosed it's always like a closed loop, but here we
yeah.
are only taking only one line.
No, I told you, right? Even I can take a closed loop. There is nothing is there outside, right?
But the length will be in that case Means
No. Even if you take a closed loop, there is no magnetic field here. There is no magnetic field here. Length will be there.
okay.
Your H will be 0, right?
Yes, sir. Yes, sir. Got it.
Correct. So in that case, what will happen? Even if I go in this particular loop, it is equal to the integral from A.
Yeah. Got it, sir. Yeah, we'll
Yeah.
split that loop.
Correct. Yeah. So now the flux per each turn is equal to mu A into MMF divided by D. So I can say the magnetomotive force is said to be D divided by mu A into phi. So I can say the MMF is also said to be, I can define some constant reluctance into phi. So this is your basic Ohm's law in your magnetostatics. So by comparing these two, I can say the reluctance is nothing but D divided by mu A. So you have to focus more here, concentrate more here. So first you have to understand what I was trying to understand here was, I was trying to formulate the basic Ohm's law in magnetostatics. So to formulate, I was in your electrostatics, you are having this relation. V is equal to R into I. So voltage is equal to resistance in I. So in the same way, I was trying to formulate a Ohm's law for the magnetostatics so that I can put everything in a circuit analysis form. So that is the reason why the magnetomotive force I was able to represent with some constant reluctance. So the reluctance by comparison, I can say D by mu A. So you can see here D is the length of the solenoid and A is the circular area of cross section. So first of all, can you tell me what is the resistance meaning in electrostatics in your networks? What is that actual resistance does in a circuit?
It opposes current flow.
Correct. In the same fashion here, the reluctance is the property of the magnetic core which opposes the change in the flux. Okay, you can see here the reluctance, whatever I seen here, it is same as your V is equal to R into I. So this opposes the change in current and the reluctance opposes the change in flux. So when you try to pass amount of current through the magnetic core, there will be a magnetic flux which will be generated, right? So how that magnetic field will be controlled or the magnetic flux will be controlled is based on the reluctance property of this. So the reluctance is a property of the magnetic core to oppose the generation of the magnetic flux. So suppose if a magnetic circuit is having more reluctance, higher value of reluctance means your flux will be less. That's it, right? So higher value of reluctance means you can easily see here your permeability will be lower. So when the permeability is lower, your flux cannot be concentrated, flux cannot be created. Yeah. So whatever the same magnetic circuit I have given in a physical model, I was able to replace it with the electric circuit. You can see here something like this. So where the source is nothing but your MMF itself. So which is nothing but N into I. We already seen that. Into the entire core can be replaced with the reluctance. And you can compare this, instead of current, you are having your flux. So there will be a flux. So what I was trying to represent, whatever the magnetic circuit here, I was trying to put it in a circuit model. So I will try to make it still clear. See, suppose if you have a conductor and you try to apply voltage here. In electrostatics, how will you represent this one? The conductor is having a resistance and you are going to apply a voltage. So this is your voltage or the EMF and this is the resistance of the conductor and there will be a current flow. In similarly, how to represent this magnetic circuit? Same way, instead of your EMF, I was going to represent with a magnetomotive force. And instead of resistance of this conductor, I have the reluctance of the core itself. So I can replace it with the reluctance of the core. And instead of current flow, there will be a flux. There will be a flux which will be developed here. So I can say there is a flux. So you can see here in the electrostatics, you can apply the Ohm's law. So whatever the voltage I was applying here, it will be the drop across the resistance. So what is the Ohm's law here? It says V is equal to IR. Similarly, if you apply the same Ohm's law here, what you are going to get? The total magnetomotive force will be the drop across this reluctance. So the basic Ohm's law in magnetostatics was MMF is equal to the reluctance times the flux. And you can see here in electrostatics, the resistance will be defined as rho L by A. Length of the conductor and area of the cross section. Similarly, how the reluctance is defined here? D by mu A. So D is the length of the solenoid and A is the circular area of cross section. You can see here there is an analogy between the electrostatics and the magnetostatics. Are you getting that point? Comparison? Is that A is potential? What potential it is? No, I told you A is nothing but area of cross section here. A is the cross section of the solenoid. Any questions here? So the magnetic circuit I was able to represent in terms of your circuit model. So what I mean to say, if any magnetic circuit is representing in a physical model like this, electrically it is represented with a magnetomotive source, which is nothing but number of windings into I, and the core is replaced by the reluctance. So in that reluctance, we already seen D is the length in which the flux is coupled. So in this case, the flux is coupled from here to here. So D is the total mean length in which the flux is contained. And similarly, A is the circular area of cross section. So what will be the area in which the flux is passing? So that is nothing but your reluctance. So can you tell me what is the unit of reluctance quickly? What is the unit of reluctance? Quickly. So what is the unit of reluctance? Just now you can see the Ohm's law only, you can tell. Magnetomotive force is equal to reluctance times the flux. So the magnetomotive force is nothing but N into I. Right? Now can you able to tell what is the unit of reluctance now? You can see these two. What is the unit of reluctance then? Anyone? What is the unit of reluctance?
Ampere by Weber.
Ampere per Weber, correct. But generally, if you see the textbook, they will call ampere per Weber. Because actually tons is not an SI unit. Just to represent N, N is nothing but your number of tons, right? So they used to put ampere turn per Weber. But if exact SI model, that is nothing but ampere per Weber. That is correct. But tons has no significance. So the tons they will be adding just to account for the number of tons N. So if you see the textbook, they used to give sometimes ampere tons per Weber, or you can say simply ampere per Weber if it is 1 ton. Okay. So next we will see some of the magnetic simple circuits, and we will try to put it in a model. Okay, you can see this diagram. So this is nothing but your simple, you have seen your transformer course and all, electrical people especially. So if we have a transformer core, it will be purely made up of iron. So suppose if I say one side I have taken n number of windings and I was passing a current of I. So what will happen? So this is the current direction in which current is flowing. Can you tell me what will be the direction of flux here? The flux is linking in which path? So since the current is flowing here, the magnetic flux will be perpendicular. So the flux will be generated here, and the same flux is linking in all the dimensions of this magnetic core. So this is the path for my magnetic flux to flow in the circuit. Right. Now I want to represent this circuit in case of a model. How to represent? Whatever the number of windings, you know that N into but the MMF which is created in the circuit. So this is same as your MMF. So which is nothing but N into I is equal to the most the flux is passing here, it is covering the entire length, right? This is going to make an entire loop. So I was assuming that the core is uniform in all the dimensions. So what is the meaning of that? You can see here at this particular side, this is the cross-sectional area. So even if you see on that, I was assuming that there is the same cross-section area here. And there is the same cross-section area here. So in that case, what I will do, the total magnetic core when you are surrounding, I can say the total magnetic core is having a reluctance of rho. This is the reluctance of the core. And how to define the reluctance of the core in that case? The reluctance of the core is nothing but the length of the solenoid divided by mu A. And you have to answer me this question right now. What should be the length of this one? Will you consider from here to here only? Or will you consider from to here, the total length? So what is this D represents? It is one side of the magnetic core or the total length of the magnetic, which is correct? Total length, good. So this D you have to remember here, because as I mentioned, the area of cross section in each dimension same. So this D represents the mean length in which the flux is flowing. So you can see here the flux is flowing in this path. So you should consider this whole length. So that represents your D here in this case. So whereas if you have a solenoid, the flux is confined from here to here. So that is the reason why straight away you taken length as a parameter. But in this case, the flux is flowing in this whole magnetic flux path. So this is your mean free length. So D is nothing but the total length in which the flux is contained. So you have to be specific about that. If the flux is confined to only one side, then you consider only one side. If the flux is making a whole loop, you have to take the whole loop area. Loop area as well as a whole length. It is called the mean free length. So D is basically technically speaking to be mean free length in which the total flux is contained. So you got the point here right now? So I will give an exercise to you. So take this magnetic circuit and put it in a model.
So, so you like what we came across till now is when current, like if current is in this loop, so there's a perpendicular flux. But
Correct.
in this particular case, you said it's in the entire core.
Yes.
So how is like
No,
there's no
no,
the
see,
coil is not around the entire core, right?
correct. I was telling about this one. See, whatever the dimensions of this core is guiding the flux to go in that direction. See, because iron is basically said to be a conductive material. See, whenever the flux is generated,
Okay,
since
okay.
the boundary is restricted here, it is getting diverted to the other dimension.
Okay, so it
Because your
flows
magnetic
throughout
core,
the core.
yeah, your magnetic circuit design is something like this, right?
Yes.
Okay, the moment once the flux is generated, it cannot go out because this is a conductive material. So the shape of the magnetic core itself is guiding that the flux should take the diverse, you can say the different path. Okay.
Okay.
So suppose when you have a toroid, see what happens here, because the flux is contained here, so there is no obstacle, so it is making a loop. But what will happen? The shape of the magnetic core itself here, the shape of the magnetic core itself is like this. So what will happen when the flux is reaching here? It will not go out because outside there is an air. So the shape is guiding that the flux is diverted in this fashion. So once again it reaches here, there will be air here, so it is getting diverted. So the shape of core is diverting the magnetic flux to make a loop. So you got my point?
Okay. So then in that case, even in case of a toroid,
Yeah.
uh, you even like if we do not, if the current does not flow throughout the toroid, suppose we stop the coil at half the
Yeah.
toroid, even then the current, the
Exactly.
flux
Even
flow
then
out.
also, whatever the number of windings will there, that will be there, but the flux will flow through the entire area.
Okay, 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 sir.
Okay.
Fine.
If suppose you are making windings only up to here, but whatever the flux is confined here, it is going to make throughout the core. You need not to complete the whole area of the toroid. Okay, understood?
Okay, sir. Okay, fine.
Yeah.
Yes.
Now, I want this to be represented in a magnetic circuit model. So first of all, can you tell me in this case, whatever the flux it is generating here, you can see here, till up to here the magnetic core is there, and between this one and this one there is a small air gap. So whatever the flux is generating here, it will pass through the core, and some amount of flux is passing through this air gap also, and it is making a loop. And what will happen when it is moving out of the core and it is entering the air gap, there will be some fringing fields. So the magnetic flux lines are tending to be expand in this particular region. So that fringing fields I was not considering here. I was making sure that the magnetic flux is uniform. So which means that whatever the flux generated because of this magnetomotive force, it is going here and making passing through the core, as well as the same flux is passing through the air gap. So in that case, I want to model the circuit. How to model? So first of all, what is the MMF created in the circuit is same as your Ni. So it is not going to change. And whatever the flux which is generated due to the current passing through these windings, there will be a part of the flux which is flowing through the core, and there will be a part of the flux which is going through the air gap. So there are two different mediums comes in picture here. So whenever two different mediums comes in picture, you can account those two different mediums with the reluctance of the core as well as the reluctance of the air gap. You understand my point now, everyone? Because whatever the flux it is generated here, it is confined to the core as well as the air gap. So that is the reason why the core I have considered with a reluctance of the core, and whatever the gap between these two is accounted by the air. So there are two reluctances comes in picture, and these two reluctances are in series. Why? Because the same flux is flowing through both the core as well as the air gap. So similarly, if the current is flowing in a circuit which is same, means two elements are connected in series, then current remains same. Similarly, the flux in the core and the flux in the air gap is same. So which means both are connected. So the overall reluctance is also getting to be additive. Now, this is the flux which is generated, which is passing through the core as well as the air gap. So you can apply the KVL now. So what is the Kirchhoff's voltage law says? Whatever the total MMF created in the circuit is equal to the drop across the core material as well as the air gap. So what I can say, the total flux phi into reluctance of core plus the flux into the reluctance of air gap. So I can say the total Ni is equal to phi into the reluctance of the core plus the reluctance of the air gap. So what will be the overall reluctance? You can see here, this is of the form Ni is equal to phi into the overall reluctance. So the overall reluctance, I can say it is nothing but reluctance of the core plus air. So that's what you have seen in your electrostatics. Two resistance connected in series, the overall resistance will be additive. Similarly, if two mediums are connected in series, the overall reluctance is also going to be additive. So what I mean to say here, whatever the Ohm's law, KVL, KCL, you are doing in your electrostatics, you can do the same thing in your magnetostatics. So in that case, your problem becomes simpler. So that is the reason why we are modeling the magnetic circuit and analyzing in terms of your circuit theory. So in this case, what is the reluctance of the core and what is the reluctance of the air gap? You have to define. So the reluctance is d by mu into A. So you can see here the reluctance core, if you want to define, that means you have to consider the length from here to here and here to here before the air gap, and again from here to here and making a loop. So you should consider the whole distance of the flux which is passing through the core. That I was calling it as a mean free length of the flux divided by mu into the area of the core. I already given here A into C. Sorry, AC. AC is the circular area of cross section, or you can say cross sectional area of the core. Similarly, the reluctance of the air gap will be, so the air gap is present for a length of G itself here. You can see here the air gap length is G divided by mu is nothing but mu naught for air gap into the area of cross section. You can see here same as this one. You can see here AG. This is the area of cross section of the air gap. So any questions here? So did you understand these parameters? Reluctance? Why the length of the core is called the mean free length? So the mean free length is basically represents the length in which the magnetic flux is confined. So simple. See here, when the magnetic flux is generated here, it will flow here and it will flow here and it will come here. As per the core part is concerned, again it will start from here and it will go here. So whatever the length in which the magnetic flux is moving, that I was calling it as a mean free length. So it is nothing but the length of the core itself, because when you are moving from here to here and here, it is nothing but the length of the core itself where the flux is completely confined. So that is called my mean free length. You understood?
Sir, AG and AC will be equal, right?
But that actually, so what will happen when, let me write here differently. Okay, so whatever the flux which is coming out here, as I said, right, it is going to bend here. That is called fringing effects. That time what will happen? The flux may not be confined to the same area of cross section here. The flux can expand somewhere this side and this side. So that time the area in which the flux is contained may be slightly different. But ideally speaking, if you are neglecting the fringing effects, the area of the air gap and the area of the core remains same.
Okay, means we can consider them equal while solving
Equal.
problems.
Yes. If while solving problems, it is clear, because while solving problems, always they will give you that the fringing fields can be neglected.
Okay.
Okay. In that case, you can consider same. Or they will clearly give in the problem also what is the area of the air gap and what is the area of the core. Both they will give.
Okay, sir.
Okay. And somebody is asking here the length of the core won't be dg. What is the d into g? So g is nothing but the length of the air gap. Okay. D minus g. No. No. What actually D represents? So the reluctance of the core, once again I was telling, the reluctance of the core is nothing but the mean length divided by mu A. Okay, I will give some simple example. Let us say from here to here there is a 3 meter, here there is a 4, and here to here there is 3, and air gap is 1 unit, and this one is 2, and this one is 2. So can you tell me what is the mean length in this case? What is the mean length of the core? I was talking about mean length of the core. It is simple. Mean length of the air gap is straight, because the length of the air gap is, I have given 1 unit. What is the mean length of the core? So in other than air gap, the flux is passing through how much length? So that will be 3 plus 2 plus 2 plus 3 plus 4. So 5, 7, 10 and 14. So this is your mean free length in that case. You got my point? Yeah. Once again I was telling, this d is nothing but the length in which the flux is flowing. because inside a core, the flux is passing through all the core length. So that is the reason why you calculate the sum of all the total length that give the mean free length. And similarly, in case of a air gap, it is very simple. The flux is confined for only one small area, small length. So that you can gap, you can consider it as G. Okay. Okay. And the next thing we'll see in the problem, then you can understand it better. No need to get confused now. So on the last topic, we'll see the Faraday's law. So in Faraday's law, I have given clearly the example here. So consider that this is a coil, and of course there is no current flowing through the coil initially, and I have connected a galvanometer to this particular coil. And what I try to do, I will try to bring a magnet, and I was moving to and fro here. So I was taking a magnet and bringing it closer to the coil and moving away. So something I was making an oscillations of this magnet. So that time what will happen, even though there is no current in this coil, the movement of this magnet is going to create a voltage in this loop. So that's what you can see the deflection in the galvanometer. So the moment once you move the magnet to and fro, you can observe that the galvanometer indicates reading. So that is what is given by the Faraday's law. So what is the Faraday's law says that, so whenever you are moving the magnet to and fro, there is a continuous change of flux with respect to time. So you are moving to and fro means there will be a magnetic field disturbance which is changing with respect to the time. So that change in the flux is creating some voltage in this particular loop. So mathematically speaking, what is the Faraday's law says? So whatever the voltage induced in the loop is nothing but the rate of change of flux with respect to time. So why the flux is changing here was because you are moving the magnet to and fro. So continuously your flux lines are getting. So the change in flux with respect to time is going to create an additional voltage in this circuit that is called your Faraday's law says. And you can see in your real-time applications also. So I will give one example. Suppose you have designed a particular circuit and you have a resistor, inductor and capacitor. Okay, and let me connect some ammeter in series here. I was applying some 100 volt and now 1 Henry and 1 Farad. So initially what you will do, you will try to measure the current in this circuit using your KVL. Okay, you will get a finite value. I don't want to comment on that. Now what I will try to do, I will try to bring a current carrying wire, and I was trying to make very close to this particular circuit. In that case, what will happen? Will your ammeter reading remain same? So suppose before this current carrying wire is there, you may get a current of 10 amperes. Okay. Now, I will bring this current carrying wire and I was passing on time varying current. So what happens to this ammeter reading? Will it remains at 10 ampere or the current reading will change? Does the current in the circuit changes or will it remain same? Change. What is the reason? What is the reason? It's simple. Whatever the current which is passing here, you are passing a time varying current. So the time varying current is going to create time varying flux. Correct. Because every current carrying wire will create a magnetic field. So if you pass a time varying current, the magnetic flux is also time varying. So whenever there is a change in magnetic flux using your Faraday's law, there it is going to create an additional voltage in the circuit. So instead of whatever you are applying voltage here, it is going to create some extra voltage. So that is the reason why you can see there is a deflection in the ammeter. Okay, and all your interference problems and all is the consequences of your Faraday's law. Suppose in your home also, if you are having a television and if you are having a grinder or electric mixie and you try to switch on that mixer, what will happen sometimes, you can see there is a blur which is observed on the display of your television. So what will happen when you turn on your motor? So that motor is the source of your magnetic field emissions. So those emissions are varying with respect to time. That is going to create some noise inside your electronics of your television. So that is the reason why you will get some kind of disturbance on the screen. So all other electromagnetic interference problems is mainly due to the Faraday's effect. So you understood right now what is the Faraday's losses? So whenever you are disturbing the flux or whenever there is a change of flux with respect to time, you are going to get an additional induced EMF. So in other words, what I will say, when you go for the time varying fields, your Kirchhoff's voltage law will not be applicable. Is my statement correct? When you go for the time varying fields, your Kirchhoff's voltage law is not applicable. Will you agree with my statement? Is my statement correct or not? You got confused? No. I said yes. But your network professor said that even if you, just a second. So even in your networks also, you have a time varying current, which is a time varying current, and you have your resistor, inductor, and capacitor, right? And in that case, you have applied KVL only to find out what is the current, right? But what I was saying straight away, KVL is no more applicable when it is time varying. Your network professor said that KVL can be happily applied. But I was saying that you cannot apply the KVL when you go for the time varying fields. So who's telling the correct statement? Me or your network professor? KVL can be applied, sir. But I was strictly saying, I was insisting my point, your KVL cannot be applicable. KVL can be applied. What will be the reason? You can speak here, at least others can also listen to you.
So, like, we use the KVL rule in the circuit, but
Correct,
I don't
correct.
know.
Just now I have explained you, right? What will happen when I bring a current carrying wire and I place close to the circuit? In that case, will your current will match according to KVL?
No, sir. In that
That's
case,
what
it
I
won't.
said, right? So that's what do you mean by time varying? So you can apply the KVL as long as there is no sources of magnetic field nearby that circuit. If you are trying to bring a current carrying wire, which is making sure that it is going to create an additional EMF, so your KVL is no more valid. So in your networks, you are making an assumption that there are no sources of magnetic field nearby. So what is the condition I given? This induced EMF is equal to d phi by dt. Okay, in your network, when you are doing, you are assuming that there are no sources of magnetic field, which means that there will not be any magnetic flux in that region. So in that case, your induced EMF is 0. So that time we can apply. And at the same time, suppose if I have a current carrying wire and I will pass a DC current, will your current in the circuit changes? So this is your original circuit and I will try to bring a current carrying wire by passing DC current. In that case, the current in your circuit changes or remains same? No changes. Same. The reason was?
The
What is the
DC is
reason?
not time varying.
Yeah, because whatever the current carrying wire you are passing, this is your DC current. Since if it is your DC current, the flux is also independent of time, which means that the flux is also constant. So whenever there is no change in flux, your differentiation is 0. If the flux is constant, the differentiation will be 0. So there will not be any additional EMF. But what if you pass a AC current through that wire, and if you place very nearby that circuit, your KVL is no more valid. So the general statement was the Kirchhoff's voltage law you should not apply for time varying fields except under certain circumstances. So those 2 points I have given. So in your network, whatever the professor said, that is just by assuming certain conditions. So what is that condition? There are no sources of magnetic field and in the presence of a constant magnetic field. So these are the two conditions only where you can apply your KVL. So as long as you place your circuit in which there is a change in magnetic flux, your Kirchhoff voltage law is not going to be valid. So you got the point now? Conclusion? So clarity is there or not? Still anything clarity is missing here?
That
Yeah. Yes.
inductor we apply normally the voltage from the voltage source. So you know that the inductance formula that phi equals to Li. So if this di dt will be there, then automatically voltage will be induced there. In that case, we solve the equation using the KVL only. So in that case, as there is no external force like this occurring here, that's why there is no problem to apply that equation, that KVL.
No. That's what you can see here. Through next chapter, what we are going to discuss, there is no, it's not a physical inductance which is present there because whatever the flux it is passing through the air, right? It is not passing through the solenoid and it is not passing through the toroid. So your inductance value is not defined. Okay. In that case, what will happen? This is continuously, it is something like a leakage flux, you can say. It will vary from one time to time where you cannot fix the value of the inductance. So it is something like a disturbance, right? It's something like an interference. Okay. So the same thing I can explain you in the real time. I told you, right, in the previous case, when you switch on the mixer, only for the initial some amount of time, you will get a more blurriness in the display. After some time, it will get stabilized. So as per your case, okay, if it is going to create a constant voltage because of the finite inductance, the disturbance should be continuously present.
Yes.
Yes, it's not happening. Because of what reason? The inductance you will not be able to define there. Okay.
Okay, it is missing, right? That
Yes,
flux
it
is
is
missing in
missing.
the air, so that it is permanently
Correct.
not present.
Correct. So it is something like an interference that is causing. Variation of the flux is sometimes from time to time it is varying. So you cannot predict what will happen the magnetic flux after t is equal to 5 seconds or 10 seconds. It's not a predictable. So once the inductance is there, you can predict what is the flux over the time.
Okay.
So in this case, the flux cannot be predictable, but there is some kind of disturbance is there. That is what it says.
Okay.
But if there is a finite inductance, what you said was correct. It is going to create a fixed amount of the voltage in the circuit, additional voltage. That time your KVL you can apply.
Okay.
Okay. So any questions as of now in today's discussion? Okay, we'll try to derive it one of the equations. So what is that Faraday's law says? The induced EMF is equals to the rate of change of flux with respect to time. Okay, then in terms of your electrostatics, we know that induced EMF is nothing but the voltage. So the voltage is the line integral of electric field intensity in a loop. So you can see here the voltage is induced in the loop itself and the loop is closed. So whatever the voltage induced in this loop is equal to minus d phi by dt. And there is a significance for this minus, you would have been known the reason because it is justified by the Lenz's law. So what is the Lenz's law says? The negative sign indicates that whatever the induced EMF created in this circuit, it is trying to oppose the change of the flux. So whatever the flux it is causing in which actually this flux is causing some voltage in this circuit. And what is this negative sign indicates? Whatever the voltage you have created in this circuit, it is trying to oppose the generation of the flux from this magnet. So that is what given by the Lenz's law. So whatever the induced EMF is always opposes the change in the flux, which is actually causing for that voltage. Okay, so that is the reason why this negative sign is there. So you can see here, this is your equation. And here only you can see here, that is, I told you one generic statement, your KVL is no more applicable when you go for the time varying fields. This is what my proof I have given. Because till now, whatever you have studied in static, so gradually I was moving into the varying. So in static fields, what you have studied, and integral E dot dl is equal to 0. This is what you have studied, right, till now? Yes or no? So till now we are having one Maxwell equation says that the line integral of electric field is always 0 in a loop. That's what we studied, right? Now what will happen here? That means this is satisfying your KVL because E dot dl is nothing but the voltage. So the voltage in a loop is always equal to 0. That is what your KVL. We have studied in your static fields. Now what I said, I was moving to the time varying fields. So whenever there is a time varying fields, this term is equal to 0.
Hello.
So this term not equal to 0 means your KVL is no more valid. So KVL will be valid if that term is equal to 0. But as I said in the previous case, whenever there is a no flux, we can say this term is equal to 0. So this is a
Hello.
point which strong, yes.
This is that E dot dl equals to 0 where KVL is varied, KVL is applied, that energy is conservative, they say there, and
Yeah.
here it is non-conservative. I mean,
Okay.
why it is?
That's what, see, that's what I was saying. When the energy is non-conservative, you can say KVL is not satisfied. Okay. That's what the equation, when I say integral E dot dl is equal to 0, which means that whatever the source voltage it is there, that is completely absorbed by the load. So there is
Okay.
no missing of any voltage, right?
Okay. Okay. Yes.
Now in this case, it is not equal to 0 means there is something is there. Still something is there. Source is producing something, load is absorbing, but there is some other term is there. So which is nothing but the
Other
voltage is
partial energies that is not produced by the source.
correct. That is what I was saying. It's a non-conservative field. That is the reason why your KVL is not applicable. If you say
Okay.
KVL is satisfying, it should be conservative. Electric field is said to be conservative.
Yes.
That time, straight away, you can say E dot dl is equal to 0. But since it is having a finite value, I can say that when you go for the time varying fields, the electric field is said to be non-conservative. So your
Okay.
integral E dot dl is not going to 0, not going to be equal to 0. That is due to the rate of change of flux with respect to time. So what is the condition you got? Whatever the induced EMF you have created is the rate of change of flux with respect to time. So what is your Stokes theorem says now? So whenever the line is closed, you can convert it in terms of your surface integral. So the same equation, I can convert it something like this. Curl of E into ds is equal to minus d by dt of, the flux can be written as the flux density multiplied by area. And you can rearrange the equation. So curl of E into ds is equal to double integral. D by dt I will send inside. So you can say dou b by dou t. Because why I am writing dou b by dou t, already there is a one variable is there. This is my another variable. So when you are sending this d by dt, because d by dt can be applied only for flux density. Because surface is not dependent on the time, right? So d by dt is applied only on the b, and I was replacing dou t because already there is another variable ds. So by comparing these two, what you will get, the curl of electric field intensity is equal to minus dou b by dou t. So this is having a specific meaning here. This you can see here. The time variation of the magnetic flux density is going to create a spatial variation of electric field. So when you go to the time varying fields right now, one of our Maxwell equation got changed. So what is that? The electric field intensity in a loop is equal to 0. Till now we have studied this. Now, when you go for the time varying fields, there is a change in the Maxwell equation. That is, integral E dot dl is equal to minus d phi by dt. In other words, in static fields you have studied, the electric field is said to be conservative. Now what you are getting, in time varying fields, the curl of electric field is equal to the rate of change of magnetic flux. So you can see here, the time variation of magnetic field produces the space variation of electric field. So which leads to the electromagnetic waves. So the time variation in one domain is producing the spatial variation. So why I'm calling it a spatial variation was, you can see curl is nothing but a spatial operator. Or you can say del is a spatial operator. So the time variation in one domain is producing the spatial variation in other domain. So in the next class, we will also see the time variation of electric field produces spatial variation of magnetic field. So when you go for the time varying fields, it seems to be the propagation of the wave. So the time variation of magnetic field produces the electric field is propagating in space. So that's how your spatial electric field is created. So which leads to the wave nature. That we will study in the next class. But as of now, you can remember these two Maxwell's equation. So when you go for the time varying fields, there is a change in the Maxwell equation. That's what given by this equation. Okay. So any questions here? So in today's class, whatever the doubts you have, you can get it clarified now.
Sir, the mutual inductance, but actually.
Yeah, mutual inductance. Huh? Okay, which one? Yeah.
Sir, means one flux is linking to another flux. Actually, not able to understand that.
Okay, I will explain here once again. See, when any current is passing through the coil 2, what happens? There will be a flux created in this circuit, right?
Yes, sir.
Now, if these two coils are nearby, what will happen? Whatever the flux generated from this, it may also cover this coil 1 if both are nearby.
Okay, sir.
Agree? Yeah.
Yes, sir.
Now, in that case, what will happen? The flux generated in the second coil is linking to the first coil, right?
Even if no current flows to the first coil.
No. If there is no current, there is no flux. There is no concept.
Okay.
So
Yes,
these
sir.
are all concepts comes when there is a current flow. Okay.
Yes, sir.
So whenever there is a current flow, then only the flux is created. So whatever the flux generated in this core, because these two are nearby, some amount of the flux will also get coupled onto these wires, okay, which is nearby.
Okay.
If both coil 1 and coil 2 are very adjacent, what will happen? You can expect 100% coupling from one coil to the other coil. But ideally, it will not happen as long as it is very nearby. Only 70 to 80% coupling will be there from one coil to the other coil. Okay.
Yes, sir.
You got my point. In that case, what will happen? How to define the mutual inductance right now? Inductance is basically the flux linkage divided by the current. Agree?
Flux linkage divided by current. Yes, sir.
Or otherwise total flux. The total flux divided by the current. So what I was defining the mutual inductance here from 1 to 2. So mutual inductance from 1 to 2 means the flux from the coil 1 is linked to the coil 2. Okay.
Yes, sir.
In that case, what will be the total flux linkage in the second coil? Ultimately, the destination is the second coil, right? In this case.
Okay, sir. Okay,
So in
sir.
that case, how to define the total flux linkage? Because there is a coupling of the flux from first to second, the number of windings in the second coil into the flux linkage from 1 to 2 divided by the current passing through second coil. Correct? Any question here?
5,122. So we'll get the value of 5,122.
Which one?
That
No,
5.
5 1 I was saying, right? 512 and 521 will be defined based on how nearby the circuit is. That's what I was telling.
Okay, they are not same, right?
They are not same. 512 and 521 is exactly equal to same provided if both are nearby. So that's what when I was doing the derivation part, what I have done, if both the coils are nearby and identical, okay.
Yes, sir.
In that case, what will happen? Whatever the flux coming from 1 to to 2 is the same if both are identical.
Okay, sir.
That I have generally called it as phi.
Yes, sir. Got it.
Okay, in that case, your M21 is also same thing. The flux generated in the first one because of coupling from 2 to 1 divided by I1. Okay. Understood?
Hello.
Yeah.
When
Yes.
that they are not same far apart,
Yeah.
that time some flux loss will be there. That's why that coupling coefficient is
That
introduced.
time what will happen? That coefficient K will be there. K factor will be added.
Mm.
Okay. Yeah. So in that case, in that question, I was saying if you are multiplying this mutual inductance, you can get it something like this. If both are identical means flux from 1 to 2 will be 2 to 1. If you are assuming that, then you can separate it. M12 into M21 will be, you can separate like this. You just multiply these two and rearrange the equations. You will get this. So as I said, phi12 is equal to phi21 means, what is the meaning of that? And both are having the same number of windings. So that case, your mutual inductance also remains same. If you are assuming one condition, phi12 is equal to phi21 and n1 is equal to n2. So in that case, your m12 is same as m21 or not?
Current through the both the loops also.
Also will be same.
Yeah, because both are connected in series only, right?
Okay.
Are you seeing here? Both the coils connected in series. Current is same or not?
Okay.
You got my point? You want me to once again explain this concept?
Got it, sir. Got it. Yes. Yes, sir. But the current flows to that loop only, right?
Yeah,
So
correct. See, whatever I have applied here, see the current, same current is flowing here because the core is same, right? The core is same. I was passing an equal current here because as long as both are connected in series.
okay, I thought like we are having two loops. Means
No, suppose correct. If you have two loops also, suppose if I apply different voltage here and different voltage here,
yes,
difference of current will be there.
yes, sir.
Okay, that time I cannot write this one. That time I
Oh,
told you, right? Whatever the flux linkage from 1 to 2 will not be same as from 2 to 1. So when
yes,
I assume that phi12 is equal to phi 21, when it will happen? The same current is flowing through both the coils. Yes or no? Hello?
yes, sir. Yes, sir.
This is my one coil. This is my other coil. So right now, as per the basic diagram is concerned, the initially both are having same number of windings and depends on what is the voltage I was applying between A to B and C to D, right? That is your question. Now, I was assuming that phi12 is equal to phi21 is same as phi. When it will happen? You could just tell me the conditions. The flux
yes.
linkage from 1 to 2 and 2 to 1 remains same if you pass the same current through both the coils or different current.
Same current and both should have same number.
Exactly. Same current as same number of windings. Agree?
Yes, sir.
Yeah, the number of windings should be same and the same current. So in that case, what will happen? The flux linkage 1 to 2. Just to understand, I have represented it as M12. Initially, I was assuming non-identical.
Yes, sir.
Okay. In that case, what will happen? M12 will be due to the number of windings in second coil into flux linkage 1 to 2 divided by I2. If I am
Yes.
assuming different thing. Okay. Now, the same way, the flux linkage from 2 to 1 will be N1 into phi to 1 divided by I1. Okay. Having different windings and different currents. If we rearrange these two equations subjected to the same flux, what it will happen? Your M12 is equal to M21 is equal to M. Phi12 is equal to phi21 is equal to phi.
Mm.
N1 is equal to N2 is equal to N. Agree?
Yes. Yes, sir.
So in that case, what will happen? If you multiply these two, this is nothing but M square. And this is nothing but N phi by I. And this is also N phi by I. So I can call this is nothing but self-inductance of the first coil. And this is the self-inductance of the second coil.
Yes, sir. Yes, sir.
Correct? These are the valid by assuming that you are assuming that 100% flux linkage. So coefficient of coupling will be, ideally speaking, 1. So what will happen in practical cases, even though if we have a same number of windings and if you pass a different currents, or the other way, same current and different windings, you may have a coefficient of coupling which will vary. So this will define what will be the efficient of the coupling. So if 100% efficiency coupling will be there from 1 to second circuit means K will be 1. Any questions still?
Got it, sir.
Okay. Still others, anybody is having question? So we'll discuss the problems related to this magnetic circuit in the next class only, because we don't have the time to discuss now.
Sir, I had a question about like the last class that you had given, last to last class you had given a sum for homework.
Yeah.
So in that I had a doubt.
Yeah. Which part? Which part?
Yes, sir. So like the first, there is the first and the fifth part. Like
Okay. This
yes,
is the part what I was trying, right? Same thing.
yes, sir, yes, sir. So the first part
So
and the
this is,
fifth
let me
part.
call it as first one, second one, third one, fourth and fifth, right?
Yes.
Because of this first and fifth, straight away there is no magnetic field, right? 0.
So I can take it 0. That is my
Yeah,
question.
exactly. Because it is lies in the same direction, right? You don't have
Yeah.
the magnetic field in the same direction of current. So straight away 1 and 5 is ruled out.
Okay. Okay.
Okay.
Yes.
Sense of 2, what will be the value you are going to get? This is D, right? And this is D by 2. Okay.
Yes.
So what is the value of alpha 1 and alpha 2? Draw a line from the starting point to the origin. So since it lies in the same direction, your alpha 1 will be 0. So when you are
Yes, sir.
seeing for the second wire, your alpha 1 will be 0. Okay. How to
Okay.
find out alpha 2? Draw a line from the end point to the observer and
Yes.
measure the angle with respect to radial line. So this will be anti-clockwise, right?
Okay. Okay.
Draw a line from the origin to this point, measure the angle with respect to radial line. This is your radial line, right?
Okay. Yes, sir. Yes, sir.
So the
I get
arrow
that.
should pointing out to radial line. So you can apply
Okay.
the trigonometry, right? You can find out what is the value of alpha 2.
Fine.
So alpha 2
Yes.
in this case is positive, right? Because you are measuring the angle in anti-clockwise, angle is positive.
Yes, sir. Positive.
Correct? Correct? Okay.
Yes, sir.
You can apply the trigonometry, right? You can find out what is sine alpha 2 and alpha 1.
Yes, I'll
Agree?
do that.
Then because of 3, what will happen? What is the radial line now? This is your radial line. Agree? This is your radial line.
Yes, sir.
And draw a line from starting point to this observer
Hmm.
and measure the angle towards the radial line. So when the arrow is pointing towards the radial line, in this case, what happens? Alpha 1 is negative or positive?
Positive.
Alpha 1, you see here. Clockwise or anti-clockwise?
And clockwise, so it will be negative.
Yeah. So draw a line from the starting point to the observer. When you are measuring the angle towards the radial line, you are moving clockwise. So when you are moving clockwise means you know that negative, right? You can apply the sine alpha 1, right? Same trigonometry you can
Yes,
apply.
sir.
So this is D and this is D by 2. You can calculate the hypotenuse. Okay.
Yes.
Similarly, what about alpha 2 here? Draw a line from the end point to the observer and your angle will be towards the radial line.
Okay.
So this time you are going anti-clockwise or clockwise? You are measuring alpha 2.
Anti-clockwise. So it'll
So
be positive.
anti-clockwise means positive. So you can do the same exercise, do the trigonometry and find out alpha 2. So similarly, what will happen for 4? This is
From
your
the
starting point, right? First, draw the radial line. This is the observer and this is your current. So radial line will be like this. And draw a line from the starting point to the observer. This is your starting point to the observer. Measure the angle here. This is your alpha 1. Agree?
yes, sir.
So arrow should point to radial line always. You should keep it in mind. This one. So in this case, when you are going in this way, you are moving clockwise or anti-clockwise?
Clockwise. So
So
it'll be
clockwise
negative.
means it is negative. So what about alpha 2?
0.
Alpha 2 is this is the end point. This will be 0. So you know that, right? Everything now?
Yes. Yes, sir.
So you can get, and I think this is the value you will get. You can verify it. After doing that, you can verify this is the answer, what you are going to get. Root 5 I by 2 by d.
Okay, fine.
Okay, yeah.
Okay, sir.
Good. So
And
any
sir,
questions other
actually,
than? Yeah. Okay.
the assignment 1, question number 5 and question
Okay.
number 6. So question number in case of E1,
Yeah.
I calculate if I have to calculate the distance, what I should do is from if I keep an observer point. So
No,
the
first of all, I
distance.
don't have the assignment right now with me. Can you say what is that question? Read out what is the question. I can able to recollect.
Okay, 1 second.
So anyhow, others, if you don't have any question, you can sign up. Not a problem. Whoever wants to discuss, I can discuss here. Others, you can sign up. Not a problem.
So do I read the question?
Yeah.
2-point charges plus 4 and minus 4 nanocoulomb are located at 005 and 00 minus 5 respectively in free space.
Okay.
Then the
Okay.
direction of electric field intensity at 0 minus 40 will be in
Okay.
which direction?
Okay. So see here, this is your positive side and this is your negative side, and the observer
Yes.
located on the negative y-axis, right?
Yes.
0, minus 4, comma 0, correct?
Yes.
Yeah. First here there is a positive charge. Can you tell me what is, and here there is a negative charge. Okay.
Yes.
And what is the direction because of this charge now? This is your source and this is your observer, right?
Yes, sir.
So what is the shortcut I told you? When the charge is
The
positive,
away.
electric field is from source to observer.
Yes,
Agree?
sir. So here will
Correct?
be so yes, sir.
This is the direction, right? This is the direction in which
Correct.
E1 will lies. Correct? Agree?
Yes, sir.
What about because of this one? This is your observer and this is your source. Correct?
So observer to source.
Yeah, observer to source. So observer to source means this will be like this.
Yes, sir.
So this is your first vector like this, and this is your second vector. So when you
Okay.
have two vectors, what will be the resultant? Resultant will
E1.
lies in the middle. No, it is simple. When you have two vectors, something like this, A bar and B bar, what is the resultant vector of A bar and B bar? It always lies at the middle.
Okay, okay. Oh,
It's a
so we
basic
applied
vector law of
that.
addition. The same logic, right? So
Okay.
this is your second and this is your first. So you can get the resultant will be downwards. Downward means it will be in negative z.
Okay, fine.
Understood? If
So,
you
so
have any
here
doubt,
I can't do. So can I do E1 plus E2 also
correct.
here?
So you tell me even what is the value? Some magnitude will be there. I
Uh,
will ignore that k factor.
so
Okay.
okay, so I took E1 from that minus 4 coulomb. Okay, so my E2. Okay, E2 is 4 AY plus 5 AZ.
No, let me write even here as per this. Even when you are writing it here, this is the vector, right? This is your E1. Agree?
Yes. Okay.
That means
Yes,
source
sir.
to
Minus.
observer, right? So this is the end point and this is my final point. Agree?
Yes, sir.
So what is the vector you are going to get? 0, minus 40, minus 005. Correct?
Okay. Okay, sir.
So in that case, what you are going to get? K factor, you can assume 1. You can ignore that. So what you are going to get? 0, minus 4 and minus 5. This is your first vector. Divided by
Yes.
that modulus. Modulus I am not going to worry. Okay? Because the distance from here to here and here to here both are same.
Okay.
Okay?
Okay, so
Now
then
what
I
about,
got it.
yeah.
So
E2
I
also, how to
have
write
made
E2?
E2 will be 0, 0 minus 5
Minus 5
minus
minus
0
0 minus
minus
4
4,
0.
0. Yes, sir.
Correct. So in that case, what you will get?
Minus 5 plus 4.
Correct. So in this case, x component, y component get cancelled. You are going to get only z component, right?
Yes, yes, sir. Okay.
So it will be negative z because of this minus.
Okay.
Sir,
Yeah, yes.
But if we do like the first E1 will be from 0, 0, 5 to 0, minus 4, 0, right, sir?
Correct. It is going in this
Yep.
way. The same
Yeah,
thing I
but
was extending down.
yeah, but while subtracting, we are taking as 0, minus 4, 0, minus 0, 0, 5.
No. See, this is a vector, right? Once again, I will write here. So this is the source point, right? And this is your observer point. Agree?
Yes, sir.
This is 0, minus 4, 0. And okay. And this point is at, what is that point I given? 0, 0,
0,
5.
0,
5, huh? Okay.
yes,
In this case, what will happen? Vector will be pointing from source to observer like this. This is your E1, right?
yes, sir.
Because this is positive here. When the charge is positive, the electric field is from source to observer. Agree?
Yes, sir.
How to write this vector right now?
So,
The
but we
vector.
usually take as a final point minus initial
Correct.
point,
In
right?
this case, what is the final point here?
0, minus 4,
That's what I've written here, right? The final point minus initial point is 0, 0, 5. I have written E1 for that only, right?
yes, sir, yes, sir. But
Yeah.
if we
When you
take
are
the
writing
theta,
E2,
we'll get it as a positive z direction.
okay, in that case, I'm sorry, I didn't get you. So E1 is correct. This is correct only, right? Is it
Yes,
correct?
sir. I just took it as the other way around and I was getting as a positive z direction.
Okay. So you have taken in this way.
No, sir, the arrow mark is proper, but while taking the vectors, I took it as a wrong.
Okay, fine. So vector will be like this: 0, minus 4, 0, minus this one. So, okay. So any questions other than this? No?
So for the distance between 2 points
Hmm.
is we do that root over x2 minus x1 whole square plus y2 minus
Correct.
we follow that formula, right? So
Yeah.
for question 6, my answer didn't match.
Okay, this is question 6.
So the 2 points were given.
Uh, uh,
A to be 2, 3, minus 1 and
A
B
is
to be 2, 3, minus 1 and B is 4, minus 50 and 2.
so minus 50 actually it is degrees. You have to remember.
Okay.
Okay, that
Oh,
actually
then
I
okay.
forget to mention there because but that is the reason why you are getting different. So this is an angle rho phi z. You should convert in x to y to z.
Oh, then okay, sir. Okay.
Okay.
Fine. That's it,
That's
sir.
it. Yeah.
Yes.
Okay, then if
Thank
you have any questions, you can make a note of it. We will discuss in the next class also. Great.
Okay. Thank you, sir.
Thank you.
Right. Good night.